Mhm. Well, hello and welcome. We're back with Gauge Theory Virtual. I'm Jiajun and colleagues. We typically start a minute late or so to give people a chance to connect. I think this semester that's going to be especially true since I teach across campus before it, and so I run over and set up the telecommunications. But we're a minute behind, and so I think we can probably get started. And so, Jiajun, do you want to try a screen share or anything? I will monitor the chat.
Yeah, so I guess
I will maybe make you a host.
Okay.
Co-host.
I mean, I'm going to share using my iPad.
Okay.
So, okay. Let's see.
And so is your iPad also called Jiajun, or does it have a different?
It's just
it
called
works.
iPad.
All right, great. I didn't. Awesome.
Okay.
Take it away.
Okay, so thanks for the invitation. I'm really happy to be talking at this seminar. So the title of my talk is a new gauge theoretic construction of four-dimensional hyperkähler LE spaces. And the outline of the talk is first to say a little bit about the background and then the main construction. And then if I have time, I'll sketch the proof and say a bit more about the future directions. And also I'm wondering if the talk is 50 minutes or 1 hour.
I believe it's 1 hour.
Oh, okay, thanks. Okay, so yeah, so I'll then probably have time to sketch the proof. Okay, so then let me begin. So the first thing I want to say is some background stuff. So first of all, just a little bit about what ALE means and then kind of its relatives. So then so there are ALE spaces, ALF spaces, ALG, and ALH, K3, and T4. So then these are all the four-dimensional hyperkähler spaces, and then these are non-compact, and then these two are compact. So then so ALE stands for asymptotically local Euclidean. So then basically this means that asymptotically looks like R4. And then ALF stands for asymptotically locally flat. And then that means asymptotically it looks like R3 cross S1. And then ALG will be asymptotically R2 cross T2, and then ALH will be R cross T3. So then these spaces frequently arise in gauge theory, and in particular, I think all of these non-compact ones, will arise as moduli space of monopoles. I think some of the details are still being carefully written down, but I think that's essentially done. And then there are a few other constructions, either using gauge theory or not, realizing some of these spaces as moduli space. In particular, I think there's a kind of a new construction of realizing K3 as a moduli space in some gauge using some gauge theory that's done by Max Semmett and his collaborators. So today I want to focus on the case of ALE, and also I want to give a gauge-theoretic construction of these spaces that's somewhat similar to the symplectic vortex equations. So it's largely inspired by Hitchin's work and Kronheimer's original construction of ALE spaces, which I'm going to review next. Okay, so a little bit more about ALE spaces. So then first of all, they're in one-to-one correspondence to finite subgroup of SU2. So let gamma be a finite subgroup of SU2. Then an ALE space can be thought of as the resolution of singularity of C2 mod gamma. So gamma, since it's a subgroup of SU2, acts on C2, and then it fixes the origin. So then you get a singular quotient. But then if you resolve the singularity, then that space is going to be locally Euclidean, and that's going to be a four-dimensional hyperkähler ALE space. And so then Kronheimer's work basically says that all of the four-dimensional ALE spaces arise in this way. So there's a one-to-one correspondence between the finite subgroups of gamma with these spaces. So then topologically, you can think of this space as can be thought of as a plumbing of a disk bundle, and so the graph, the plumbing graph, which also corresponds to the exceptional locus of the resolution of singularity, is actually the same as the Makaya quiver of gamma. So then, in other words, the exceptional spheres corresponds to the irreducible representation of gamma as a finite group. So then there's some interesting relationship going on here between topology and representation theory. So that's a little bit about these spaces, how you can think of them. And then next I want to, is there any questions? Okay. If not, I want to review Kronheimer's original construction of these spaces. Okay, so Kronheimer construction of ALE spaces. Okay, so he constructs these spaces using a finite dimensional Hyperkähler reduction. So let me introduce some notations that he used in his paper. So let R be the regular representation of gamma, and then Q is going to be C2, and it's also, you think of C2 as a quaternions. And then you let P be Q tensor the endomorphism space of R. and let M be P gamma, which denotes the gamma invariant. Well, let me say, so then the subspace of P consisting of elements invariant under the gamma action. Okay, and then let F be the subgroup of elements in UR. So then this is a unitary. So then this is a unitary transformation on R. And then let F be the subgroup of this group, such that it commutes. So then it's a group of elements that commute with the gamma action. Okay, and then so then T is the scalar subgroup sitting. So T is a scalar subgroup sitting inside this group. Okay, so here's some notations. I will remind you why use them. Okay, so now so an element in M can be thought of as a pair of matrices. So M is a subspace sitting inside P. So then in particular, the elements inside P can be thought of as a pair of matrices alpha beta, where each of them lies in the endomorphism space. So if we think of an element in this way, then the action of F on this element would be just by conjugation. So it will be just the following. Okay, and F is in the subgroup of the unitary group. Okay. So then Cronheim observed that M is hyperkähler, and then the hyperkähler structure really is just coming from the quaternion, the quaternions. So then you get and have as IJK complex structures. Okay, so for example, I think I acting on alpha beta is just by multiplication by I, and then J acting on alpha beta is by this action here, I think. Okay, so M is hyperkähler, and so then this M is actually the sort of the space that where we want to run the hyperkähler reduction. So then observe that so then the action of F on M gives rise to 3 moment maps. And they're the following. So the mu1 alpha beta is the following. So I over 2 times alpha star, the bracket of alpha star plus bracket of beta star. And then
Can I ask a question? Yes.
Yes.
Is the reason that you're having alpha and beta because the gammas are two generator groups and you're just sending each generator to a matrix, or why are we having an alpha and a beta?
Yeah, so alpha, beta, it comes from the definition of P because, let me use a different color. So because M is inside P, which is equal to Q, which is equal to C2, tensor and R. So then it's just because you're tensoring this guy with C2, so that's why you get two factors.
Is one like the complex and one like the J, or should I be thinking of it as two specific matrices if I'm thinking of coming from specific elements of gamma?
So at this point, I think, oh, I see what you're saying. So yeah, so right, so for P, you just get alpha beta as a pair of matrices, but then M is also gamma invariant, and so yeah, so then you can specifically write down what properties alpha and beta need to satisfy in order for this pair to lie in the in which is kind of, you can write it down, but it's not exactly sort of
Yeah.
Yeah, okay, yeah, I see your question
Okay,
now.
thanks.
Okay.
It's quaternionic. Got it.
Okay, so then mu2 is 1/2 alpha beta plus bracket of alpha star beta star, and then mu3 is I/2 minus the bracket of alpha beta plus bracket alpha star beta star. So then each of these moment maps map into the dual of the Lie algebra of F. So then you can group all of them together to get a moment map mu, which is just mu1, mu2, mu3 from M to R3 tensor F mod T star. So then the F is the Lie algebra of F. So T is the Lie algebra of the scalar subgroup, because we're sort of working with conjugation here. So then T acts trivially. So then you can take the quotient and then you take the dual. So then mu maps into this space. Okay, and then you kind of just do the usual Hyperkähler reduction. And so then what you get, it can be formulated as follows. So then let Z be the center of F mod T star. And we can also think of these elements sitting inside the space as traceless matrices sitting inside F. Okay, so, and then let zeta be zeta 1, zeta 2, zeta 3 lying in R3 tensor Z. So then for some good choices of zeta, so for zeta lying, lying in the good set, so what this means is, so Cronheimer has a proposition characterizing what a good set, what the good set really is, which is a subset in here. Then we get that X zeta defined to be mu inverse zeta mod F is a smooth four-dimensional manifold diffeomorphic to the resolution for singularity of C2 mod gamma. And when, so the maybe remark is that if you don't let in the good set and you pick some zeta that's not in this set, then you still try to do the reduction, then what you're gonna get is possibly a partial resolution or just C2 mod gamma without the resolution of singularity. So then you're gonna get some singular space. Okay. So this is Cronheimer's construction, and then later he would show that there's also a metric which gives you which is Hyperkähler, and then you really get the ALE space. Okay, so is there any question at this point? Okay, so then if not, I will now talk about the main construction, kind of sort of taking this construction of Cronheimer's and make it Gauge-Theoretic in some sense. Okay, so section 2, the main construction. Okay, so yeah, so the goal is to realize these spaces using ideas from gauge theory. So then first let's write down the bundles that we'll be working with. So consider S3 as an S1 bundle via the dual half vibration. So what that means is just we take e to the I theta acting on Z1, Z2, so then it acts by the inverse instead of just by itself. And the reason for that is so that the associated bundle will have holomorphic sections. Okay, so then we define the following associated bundles. So let E of and R be the associated bundle of S3 with fibers equal to and R, and R is the same and R as before, which is the endomorphism space of the regular representation. Okay, so then this is specifically so then in other words, if you have PV, then it's equivalent to PG G inverse V, where P is in S3 and G is in S1, and the V is in and R. Okay. And then let E of and R gamma be, so then here we're incorporating the gamma action as well. So then and we denote this guy by E gamma to be convenient. Okay, so then this guy is defined to be, so then you basically just add the gamma action here into the equivalence relation as well. So then PV is equivalent to PG G inverse V, which is also equivalent to P gamma inverse V. and then so everything is the same, and except well, also you have gamma is an element in the finite group. And also I guess a little bit of a caveat. So then if gamma contains -1, then this definition needs to be modified slightly because -1 is also inside G, which is an element in S1. Because S1 contains -1, then you want to make sure that the action of -1 considered as an element in S1 and also as an element in gamma, they have to coincide. And so then you need to modify this definition a little bit to take that into account, but let's not worry about that. In the end of the day, you just want to have E gamma, you want to have that to be a orbifold vector bundle, and then its sections, you can just think of them as the gamma invariant sections of the original vector bundle E and R. So in the end of the day, you just want to make sure of that. Okay, so, and then we fix several choices, such as permission structures on the bundle and etc., so that we can get a connection. So we fix a holomorphic structure on H, which is E of C. So then this is the hyperplane bundle. And also Hermitian structure. So then we get the Chern connection, which we denote by A0. And so then we fix we fix this A0 as the base connection. And then this A0 can also be thought of as a connection acting a connection on the associated bundle. And then we'll use this connection as a base point, and then we can write down the configuration space. Okay. So let the configuration space be the following. So call it AF cross C infinity E gamma. So then so I'll define each term separately. So then AF is equal to A plus kappa, I don't know, kappa Delbert, kappa inverse Delbert, kappa plus kappa star del kappa star inverse, where kappa is keep using alpha. Kappa is an element in the complexified gauge group. Oh, sorry, I guess I haven't said what the gauge group is, but I'll say that next. Okay, so then this is equal to the complexification of this group map S2 mod gamma F mod T. So this is the gauge group. So let me maybe slow down, explain a little bit. Okay, so right, so here we have this this base connection. So and then this part just denotes the. So this is how kappa as a complexified element. So basically the a group of complex automorphisms acting on the bundle E gamma. So then that's just how it will act on the space of connection. So then it acts on A0 by sending A0 to this guy. And then the gauge group, the unitary gauge group is just maps from the base, which is S2 mod gamma, into F mod T. So, oh yeah, so I guess I didn't say, so if we define E gamma to be like this, then in the end, the E gamma is an orbifold vector bundle where the base becomes S2 mod gamma, whereas the base for this vector bundle is just S2. Okay, so that's why we're mapping from S2 mod gamma into F mod T. Okay, any questions so far? Okay, so, and then the infinity of E gamma, so that's, so you can basically just think of them as the gamma invariant sections of E and R. And it will also be the orbifold sections of this bundle thought of as the orbifold vector bundle, but this is maybe a more straightforward way to think of this space. Okay, and then if we have rho in the gauge group, then rho will act on a connection paired with a section, just in the usual way. So so here on the section part, it's acting by conjugation. And also for the connection part, we're dropping the base connection A0 because rho will fix A0. Okay. So then there is a symplectic 2 form on A, F, which is the following. So you just integrate over S2 mod gamma. So because these are one forms and you can wedge them and take the trace and you can integrate and get a number. So then this is coming from the Atiyah bot construction. Whereas on the section part, there are actually 3 symplectic forms. So on the section part, there are 3 2 forms. So then you have omega 1, theta 1, theta 2 being the following integral. So you have this. And the volume, so this is a volume form on S2 or S2 mod gamma. And then omega 2 is minus real part of J theta 1, theta 2, about times the volume form. I'll say what J is in a second. And then omega 3 is S2 mod gamma, imaginary part, J theta 1, theta 2 times the volume form. So here, let me define what J is. So yeah, so where for theta, a section from X into PF of P, J theta is defined to be this guy. Okay, let me maybe write it down first and then explain. Okay, so because theta is a section on the associated bundle, then we can think of it as we can relate theta with a map F, where F is some map either from S3 or S3 mod gamma into the fiber, and then okay, maybe I'm just going to use S3 mod gamma. Oops. Because I'm just talking about orbifolds right now. Okay, so the F is, so you can think of a section as a map, equivariant map F, and then, so the theta is a map where X is mapped into, mapped to this guy, then the action of J on theta is defined to be this composition. So J of P, so here, so then here this J is just the usual quaternion action J acting on P, which is a point inside S3. Then this is what that means. And then you plug this point into F, and then you take the complex conjugate. So that's how J acts on a section of the bundle. And then you can check that you get 3 simplex 2 forms, and then so then that's where the Hyperkähler structure is coming from, because you get these 3 2 forms, and then you'll get 3 complex structures. Well, I mean, in particular, 3 distinguished complex structures, and then you get a Hyperkähler structure. Okay, so let me see. Oh my, I'm taking so much time. Okay, so let me wrap up the construction. Okay, so then hence we get 3 2 forms on the configuration space, which are just the product of omega, capital omega, with each of the 3 omegas. And then we get, we can write down the following, and we can write down the following equations. So then the first one is capturing the holomorphicity condition. So then you want theta to be holomorphic with respect to the connection. And then the second one, the second equation you can write down is the curvature of B plus I over 2 bracket of theta with theta star times the volume form, and you can set it to be zeta 1 times the volume form. And then you get 2 additional equations coming from the sort of the Hyperkähler structure on the section part. And so then you get 2 additional maps, which we can write down, which is the following. So it's J theta star bracket minus theta J theta star times the volume form, and you can set that to be theta 2 times the volume form. And then the last one is I over 4 J theta star plus theta J theta star volume form equal to theta 3 times the volume form. Okay, so here zeta 1, zeta 2, zeta 3 actually mean the same thing as in Cronhammer's construction. So then over here he has zeta 1, zeta 2, zeta 3, and they are actually just the same as what I'm writing down here, except that because I'm sort of in the situation where I'm working with differential forms, I have to multiply them with the volume form. Okay, so then now you can call this 1, 2, and then 3. So then now let zeta be zeta 1, zeta 2, zeta 3, and chi zeta, and define it to be the following. So the A0 plus B theta inside the configuration space, where you have 1, 2, and 3 all satisfied, and then you quotient this out by the gauge group. Well, here I have this little tau here, which means which denotes the antipodal invariant gauge elements. So that's just a little bit of a technicality that well, you have this antipodal invariant coming up because this J, the action of J sort of on S3, that action kind of acts on the base S2 by the antipodal map. So then in the end, you want to take, that's why in the end, you want to take the subgroup that that is invariant under the antipodal map. So that's why this is the gauge group instead of the entire gauge group defined as before. And so then the claim is that chi zeta is the same diffeomorphic or diffeomorphic, but in particular, it also has it's symplectomorphic and has a metric as x zeta that's discussed earlier in Cronhammer's construction. So that's the main construction, and I'm trying to figure out how much time I have, which I think I have maybe about 15 minutes-ish, right? Okay. Any questions so far?
15 minutes more is fine.
Okay, thank you. Okay, so then I can sketch the proof, and then hopefully say a little bit more about maybe future directions. Okay, so section 3, sketch of proof. So then so I guess maybe before I do that, I want to say that usually how you want to show like usually when you want to study the moduli space of some solutions to certain PDEs, you kind of want to show the existence of solutions, and that's usually the hard part. So you have to construct solutions, but here because there's Cronhammer's construction, I have an easier time of constructing solutions because I can sort of take Cronhammer's solution and try to view those solutions as special solutions sitting inside this moduli space. And that's kind of the main sort of the main idea of the proof, which is to see how Cronhammer's solutions lie inside this moduli space. So okay, so then first we want to show that x zeta is lying inside chi zeta. So x zeta is Kronehammer's moduli space. Okay, so then to do that, it's actually not so bad. So then you set B to be 0. And then so if we set B to be 0, then we see that so then if B is 0, then we just some of the equations will simplify. So let me write down the simplified version. If we set B to be 0, then we just get del bar A0 of theta is equal to 0, and then I over 2, the bracket is equal to zeta 1, 1 over 4, this guy is zeta 2, and 1 I over 4 j theta theta star plus theta j theta star is equal to zeta 3. Okay, and then so we want to see how these equations actually gave back Kronehammer's original equations. So then first we want to interpret this condition here. So then this condition says that theta is holomorphic with respect to A0, the fixed connection. And so 1, 2, 3. Okay, so then 1 gives us that theta is holomorphic. And so then if we think of theta as a holomorphic section, then again, so theta is, yeah, I guess F is bad because F, okay, never mind. I am just kind of using bad notation here. Okay, so theta, if theta is a holomorphic section, then again, we think of a holomorphic section as a map from the sort of the principal bundle into the fiber, then it being holomorphic. So then this being holomorphic means that it extends to C2. So okay, so then lambda is holomorphic means lambda actually extends to C2, from C2 to the fiber. So usual section is just from the principal bundle S3 into the fiber, but then because it's holomorphic, we can think of it as mapping from C2 to and R. So then now you can think of this as a pair of matrices because it's mapping from C2 into and R, and then that pair of matrices sort of correspond to the pair of matrices that Kronehammer used when he defined the space M and P. So then again, we're using the same notation alpha beta, and then this will, if we think of theta like this, we can see that we can rewrite these equations now. So then 2 will turn into exactly this guy. So then it's I over 2 of the bracket of alpha star plus beta star. And also I'm dropping, oh yeah, so I'm also dropping the 2 form on both sides. So then I'm dropping the 2 form on both sides. So then this guy exactly turns into this one, and then we set it to be zeta 1, and then the last 2 equations also decouples into the second and third equation of Kronehammer's equation. So maybe let me just do a quick calculation. So then for the first one of the third pair, you have I/4 plus this one. Okay, so because J acting on alpha beta is equal to minus beta star alpha star, then you can see that so then this guy turns into I think 1/4 I/4 J alpha star plus J beta star plus alpha J alpha star and beta J beta star. And then you can simplify, and then you see that you get exactly, I think you get exactly the third moment map equation from Cronhammer's construction. So yeah, so then I think, let me go back and just see what it was like. Yeah, I think you get this one if you do the calculation. Okay, so anyways, so you get the idea. So the idea is that if we set B to be 0, these equations will give back to Cronhammer's original equation. So then in particular, Cronhammer's solutions are solutions lying inside this moduli space. And so, so then the work now is to show that those are exactly the solutions and you don't get any additional ones. So then to do that, you need some technical premise. So then first there is, you need to show some uniqueness theorems. The uniqueness theorem 1 says if two solutions, I mean here solutions, I mean the solutions of the PD. So then solutions lying in the moduli space of the gauge-theoretic constructions. If two solutions lie on the same complex orbits, then they are gauge. They are unitarily equivalent. So that's a typical thing you can expect. And the uniqueness theorem 2. So remember, in the end, we have to use the antipodal invariant gauge group. So so that's what uniqueness theorem 2 addresses. So then it says that if two solutions lie on the same unitary orbit, they are sort of they also lie on the same antipodal invariant gauge orbit. Okay, so we have these two uniqueness theorems. So then with these two uniqueness theorems, you can argue that indeed Cronhammer solutions lie inside the moduli space as an open set. So that's the first thing so then in the end we can conclude that X zeta lies inside chi zeta, and then to argue that there aren't more solutions, you want to, so how you want to do that is to show that suppose you have more solutions, then they have to be of higher codimension. Also, they're disjoint from this space sitting inside the moduli space, and then you want to then show that and then you want to argue that cannot happen by showing some smoothness theorem, and then calculate the dimension. So then if you know the dimension of the moduli space, then you can say that, well, you cannot have higher codimensional component because you calculated the dimension. So yes, that's kind of the other directions. So so to show they're actually equal, we prove some need smoothness theorem and dimension calculation. So then this gives us that there cannot exist higher whole dimensional components inside this moduli space. So that will tell you the Cronhammer's solutions will give you everything. So yes, this part I'm kind of being a little bit sketchy, but this is the idea. And so yeah, that's the sketch of the proof. Is there any question? Okay, so if not, I can just wrap up by saying a little bit about future directions and things I'm trying to think about at the moment. So future directions. So so first of all, sort of the proof of the main theorem kind of really relies on Cronhammer's construction, because that's how you get existence of solutions. But then you should be able to just use tools from gauge theory to construct solutions explicitly, because the equations that are written down here, these are, I mean, in particular, I mean, like they're the first two equations, they're very similar to, say, Hitchin's equation. You can also think of them as symplectic vortex equations. And so you should be able to construct solutions just explicitly using just tools, techniques from gauge theory. So that's something that I'm trying to do right now. And in particular, I want to so give a formulation of gamma equivariant stability condition, so that we get a Hitchin Kobayashi correspondence in this setting. So the idea is that you kind of want some correct formulation of stability conditions, so that you can say that you get a solution if this if you have the stability condition satisfied. Well, it will be a stability condition of a pair, because we have, you know, like a connection paired with a section. So then, I mean, there's a lot of work being done. So on one hand, because I'm working with an orbifold, you want to use like parabolic bundles and parabolic degrees, and on the other hand, you're also working with pairs, and so then there's, I think there's work done for either side, and so I'm trying to group the two sides together and trying to formulate some correct notion of stability condition. Okay, so that's kind of the first thing that I'm thinking about. And then another thing you can do after maybe you finish figuring out the first step is to generalize this construction, to you know, more general ciphered fibered spaces. I'm going to explain what I mean. So right now, the ciphered fiber space that has been considered is just S3 mod gamma. So that's the ciphered fiber space that we implicitly have been considering, because, you know, like we started off with S3, and then it has a group action by gamma, then that gives, so this is a ciphered fiber space and has an S1 action. But then you can try to replace S3 with some other S1 bond over a Riemann surface, maybe a integer homology sphere or something like that, and then you can take the quotient, and then you can again write down the first two equations. These two equations won't make sense anymore because you won't have the quaternion action or the quaternion structure. But the first equation should still make sense, and you can study like the solutions of these two equations on that bundle, and hopefully construct some moduli space. And then another direction is to kind of study the like the topology of the moduli space using so you also get a Morse function coming from the S1 action. That's a little bit implicit here, but you do. And this, I mean, it's very similar to Hitchin's setup. He also has a Morse function on his moduli space, and he used that Morse function to study the topology of the moduli space. And I think you can do the same thing here. And so that's another thing that you can try to do, and then study the critical points of this Morse function, which should correspond to the the topology of this moduli space, which is just like the two handles are the exceptional spheres. Then you already know the topology. So then the critical point of this Morse function, you should already know what they are. And at the same time, they should correspond to the irreducible representations of gamma. And so then, I mean, I'm thinking if there's like a way to see the correspondence through this this Morse function. So that's another thing that could be interesting. So yeah, so that's all I have to say. Thanks.
Are there further any questions? We've had some in the middle. Well, we'll be back in a couple of weeks. I will wrangle up a speaker for us. I imagine Jiajun will send us notes, and I'll post the video and the notes onto the website. Well, thank you, everyone. Nice to see you.
You.